Hi everyone, I am Anthony and I'm going to talk to you today about insights into the initial colonisation of land by animals using information I got from field work this summer in Quebec, in Gaspé. And this was field work that was done from a small grant from Palaeosol last year. I'm then going to put this into context of the overall picture that I've got from looking at some Silurian Devonian successions from elsewhere in the world. So, first of all, I'm doing this from a trace fossil perspective rather than a body fossil perspective, which I realise might alienate me to a large proportion of the room. But why trace fossils? So, trace fossils have advantages and body fossils have advantages. But trace fossils occur everywhere and they're physical structures. They don't require conditions to preserve them. They're not going to be destroyed biologically or chemically. And using an example like this, you can see, if I can get the laser button, there we go. Okay, so consider a few scenarios where you have a trace maker walking along a surface, this little millipede type thing. Situation one, trace maker walks along the surface, walks off, you're left with your trace. No body fossil. You have more footprints than you have bodies, right? Situation two, your trace maker dies, so you're getting towards having a body fossil, but then the body doesn't survive. It gets destroyed, it gets eaten, it's destroyed chemically, and then you're left with just the trace. And actually, the conditions required to get yourself a body fossil into the rock record are, they're more unusual. This is because the fossil record is a record within a record. So trace fossils are an intrinsic part of the rock record, they're physical structures within it. The fossil record are fossils of particles within the sedimentary record. So putting this, using trace fossils to understand the terrestrialization process, we need to get an understanding of what's marine and what's non-marine. And this adds an extra layer of complexity because it's not actually very clear what is marine and what's non-marine. So looking at this, you can see we have a huge range of subcategories which all mean subtly different things. And there's a lot of overlap between them and it's all very confusing. It's much easier to work out what's subaerial and what's subaqueous and what's emergent. So here we see some examples of things which you can tell are definitely marine. You're seeing herringbone cross-strap, which you're only getting in fairly restricted environments. Or you see things like paleosols, where you can say, yes, this is non-marine. You're not going to get paleosols under the ocean. Whereas things like these adhesion marks, you might be getting these on beaches, you might be getting these on floodplains, all this sort of thing. You can't say whether it's marine or non-marine, and it makes things more challenging. So, terrestrialization. So the old red sandstone is a fairly good place to start, and the Canadian stuff is associated with that. So the old red sandstone has been studied for back in the early 1800s, and it's generally been used as the kind of archetypal. This is where terrestrialization is occurring. This is how we can understand the colonization of land. And that's because, oops, that photo shouldn't be there. That is because it's when we start to see body fossils of things first appearing in non-marine rocks, like this Euryptrid from the Arctic Canada, or Sardonia from further south in Canada. And obviously we have non-marine trace fossils associated with these things, or subaerial trace fossils associated with these things. And all of these rocks are occurring around this sort of similar time. So this is the timescale of when the main European old red sandstone pathologies are coming around, and it's all kind of late Silurian, early Devonian. And then the Catskill Delta is the famous equivalent site from North America. It's coming along a little bit later. But we're not seeing much overlap in this area here. We're not seeing the full kind of neat transition, and that is where the Gaspé sandstones can help us. So they fill in this gap around the Emsian up into the Middle Devonian to show what's going on beyond the first steps on land, how the communities have started to develop after the initial colonization. So, the Gaspé sandstones occur at the end of the Gaspé Peninsula in Quebec, fairly close to the famous Miguasha fossil fish Lagerstatten, which many of you have probably heard of. And I am looking mostly at this battery point formation, which again is in the Emsian, it's the first kind of real terrestrial deposits in this region, following this marine limestones of the Upper Gaspé limestone group. And this is what the typical exposure of the battery point formation looks like. Seeing you've got is all along the coast, we're seeing nice big bedding surfaces, but also you get quite a lot of stratigraphy, which is ideal for seeing as much as possible. And we're seeing three key facies here. We're seeing fluvial channel sands, we're seeing some overbank crevasse blade deposits, and we're seeing paleosols. I'll try and keep the sedimentology light and focus more on the interesting, what the animals are doing bit. But sadly, in your fluvial channel facies, the animals aren't really doing anything. We're seeing lots of this trough cross-stratification, and it's coarse, gravelly sediment, but there's actually nothing in the way of trace fossils. So these Gaspé sandstones, the battery point formation, was where the braided fluvial facies model was originally defined in the 70s. But yeah, there is no evidence of bioturbation occurring within these channel sands. Moving on to the Crossplay facies, we're seeing it's much more diverse. So it's going to be identified sedimentologically by seeing lots of climbing ripples, and it generally finds up through the individual blood sequences. And then towards the top, we see desiccation cracks on these muddy surfaces. And there's a lot more going on biologically here. So there's lots of plant material. So here we have some Sordonia that's been, looks like we had a standing shrub that's been swamped by this inflood of sedimentary material. So you can see Chile kind of branching upwards, and it was found vertically standing up within the rock. And then we also have some evidence of some vertebrates as well. So this piece of fish, suggesting that just because we're not seeing trace fossils in the rivers doesn't necessarily mean there was nothing living there. There was just nothing living within the sediment. Trace fossil-wise, there's also a lot more going on. So we have a wide variety of different behavioral styles, from things that are deposit feeding, creating these Astrophycus type traces. We've got things that are probably filter feeding, living in the sediment, like Dibracterium, and then some of these more kind of habitation type burrows. That's the Lacinoides style thing. So far more animals are colonizing this kind of crevasse blade deposits than we're seeing evidence of within channels. Finally, we have this Paleosol facies, which is fairly abundant. We're seeing thick, occasionally rooted, as we can see here, soils going on. Although the diversity of trace fossils that we're seeing is much smaller than it is in the Crossplay facies. Possibly we're seeing animals that are exploiting the nutrients being brought in by these flood events, which is why the Crossplay stuff is much more diverse. So, clicker. Now I'm going to tie this into a global picture to see how this fits in with the earlier signatures. So this is a map showing my field sites that I've worked on during the course of my PhD, and putting that into a paleogeographic context, covering lots of La Russia and northern parts of Gondwana. So looking really at what's going on in the Silurian, Devonian of the tropics and how animals are moving onto land there. And now adding these Australian sites into this timeline, seeing that even though they're fairly poorly constrained age-wise, there's actually quite a lot of overlap, again, around this kind of key interval highlighted in red, where we think the initial transition onto land was happening. So, from looking at all of these sites, we've put together a picture of what kind of key signals of the initial colonization of land were. So first of all, there are no in-channel traces. Secondly, the size of the traces in sand versus mud, we're seeing larger trace fossils occurring in sand than mud at this time in non-marine deposits. We're seeing a suite of similar trace fossils occurring kind of fairly universally across all the kind of European, North American things. And a lot of these trace fossils people might be familiar with, particularly things like Shillito and Planolites. But one you might not have heard of is polar erectness, which is a bit more unusual. But in fact, this appears to be one of the most important identifiers that occurs in these non-marine rocks at this time. So how does Gaspé fit in with what's going on in the slightly earlier deposits? Is the signal the same, or have we seen changes as we've gone from the latest Silurian up into the Emsium? So in terms of in-channel Floovio biotubation, we're still not seeing anything in Gaspé. It's very similar to what you were seeing in earlier rocks. When we're looking at the size of the traces in sand versus mud, so here we've got European in black, Australian stuff in red, and then Gaspé we've added in the green. So as you can see here, it's not really definitive whether it's agreeing or disagreeing with this. Everything is very small in the Gaspé sandstone. So it's not putting something huge in the mud, but it's not saying anything that solely agrees. In terms of the suite of trace fossils, while at first glance it might look like actually we're seeing completely different things, there's similar styles of behavior. Things are occupying similar niches. So we've still got deposit feeders with this Astrophycus taking over from this Hydalia type thing. We're still seeing filter feeders, we're still seeing miniscape burrows. But the one thing that we're not seeing is this polar erectness. So polar erectness was initially identified from the Canadian Arctic, and further as a U-shaped burrow. So it's got this thing here where the animal was occupying. And it's thought that from further work, animal was kind of burrowing down underneath the sediment to avoid drying out and when the water all disappeared, because it's commonly associated with things like desiccation cracks and adhesion marks, all these emergent sedimentary structures. And this polar erectness occurs all over the world at this time in very similar fascies. So it's occurring in Arctic Canada, it's occurring in Australia, Norway and Ireland. But up in the Emsium of Gaspé, we're not seeing this polar erectness. So it seems like it was occupying a very narrow stratigraphic time period in this kind of late Silurian, early Devonian. And so it's a very narrow signature for the initial colonization of land. So going back to the big picture, where does Gaspé fit in? Well, a lot of the signal is the same. We're still seeing similar levels of diversity in the behavior of things living on land. We're still seeing nothing burrowing within fluvial like bar forms within the channels. We're not sure whether or not we're seeing agreement here, but we're not seeing this marker trace fossil for the initial first colonization of land. So to conclude, looks like the signature of the colonization process has slightly changed, and things have animals might be more comfortable living in drier environments by the time we're getting into the Emsium, because we're not seeing this marker trace of animals burrowing beneath the surface to retain their moisture. So, thank you very much.